Hi, I'm Kathy. In this lesson, we're going to look at the tangent, cotangent, secant, and cosecant functions. Let's start with some definitions. If alpha is an angle in standard position and xy is the point of intersection of the terminal side and the unit circle, we define the tangent, cotangent, secant, and cosecant functions as the tangent of alpha, the angle in standard position, is equal to y over x. Cotangent of alpha is x over y, secant of alpha is 1 over x, and cosecant of alpha is 1 over y. We exclude from the domain of each function any value of alpha for which the denominator is 0. Well, using these definitions, we can come up with some identities. Recall that for this particular angle alpha that we're discussing, the sine of alpha is y, and the cosine of alpha is x. Well, since the tangent of alpha is y over x, we can substitute and say sine alpha for y, cosine alpha for x. Tangent of alpha is sine alpha over cosine alpha. Now for cotangent. The cotangent of alpha is x over y. Again, substituting cosine alpha for x and sine alpha for y, we can say cotangent alpha is cosine alpha over sine alpha. Now for secant. Secant alpha is 1 over x. Substituting for x, I can say secant alpha is 1 over cosine alpha. And finally, cosecant alpha is 1 over y, which, again, substituting, is 1 over sine alpha. Well, let me summarize these identities that we achieved or derived from the definitions. If alpha is any angle or real number, tangent alpha is sine alpha over cosine alpha. Cotangent alpha is cosine alpha over sine alpha. Secant alpha is 1 over cosine alpha, and cosecant alpha is 1 over sine alpha, provided no denominator is 0. Well, let's use these identities that we've derived from the definitions to find some values. First, we want to find the value of all 6 trigonometric functions for each angle, and I only have one angle written here at the moment. We want to find the value of all 6 trig functions of pi over 4. Well, let's write down the sine and cosine of that, which you should already know. The sine of pi over 4 is the square root of 2 over 2, and the cosine of pi over 4 is the square root of 2 over 2. Now let's go to the tangent. The tangent of pi over 4, some angle alpha, should be the sine of that angle, pi over 4, over the cosine of that angle. Well, if the sine is square root 2 over 2 and the cosine is square root 2 over 2, that means the tangent of pi over 4 is exactly 1. Now for cotangent. Cotangent of pi over 4 of some angle alpha is the cosine of that angle over the sine of that angle, which again is going to be square root 2 over 2 over square root 2 over 2, or exactly 1. So we have 4 of the trig functions of pi over 4. Let's look at the secant of pi over 4. The secant of pi over 4 is 1 over the cosine of pi over 4, and the cosine of pi over 4 is square root 2 over 2. So it's 1 over square root 2 over 2, which is exactly equal to square root 2. So secant of pi over 4 is square root 2. And finally, cosecant of pi over 4 is 1 over the sine of pi over 4, which, as we did here, is going to be 1 over square root 2 over 2, or exactly square root 2. Well, let's try all this again for a different angle. For the angle 150 degrees, we want to find all 6 trigonometric functions of this. Well, to begin with, recall that the reference angle for 150 degrees is 30 degrees. And so the sine of 150 degrees, which is what we're looking for, is going to be exactly the sine of 30 degrees, which is 1/2. But the cosine of 150 degrees is going to be the opposite of the cosine of negative 30 degrees. That's a degree symbol right there, which is going to be negative square root 3 over 2. So I have the sine and cosine of 150 degrees. Let's move on to the tangent. Tangent of 150 degrees is going to be the sine of that angle divided by the cosine of that. So in this particular case, 1/2 divided by negative square root 3 over 2, which is going to be negative 1/2 times 2 over the square root 3, or negative 1 over square root 3, which can be written negative square root 3 over 3. Now let's find the cotangent of 150 degrees. Recall that the cotangent is the cosine of 150 degrees over the sine of 150 degrees, which is going to be negative square root 3 over 2 over 1/2. And if you simplify this by multiplying by the reciprocal, you will end up with negative square root 3. Now we need the secant of 150 degrees, which is going to be 1 over cosine 150 degrees, which is 1 over negative square root 3 over 2, or if I multiply by the reciprocal, negative 2 over square root 3, which if you rationalize the denominator can be rewritten negative 2 square roots of 3 over 3. And finally, cosecant 150 degrees is 1 over sine 150 degrees, which is 1 over 1/2 or 2. Well, let's move on from here and look at some graphs, starting with the graph of the tangent. What we want to do to graph the tangent is make a table of values. So using a calculator, let's put the calculator in radians and evaluate the function tan x for these radian values. So you can check me with your calculator. The tangent of negative 1.56 is about negative 92.6. Of negative 1.2 is about negative 2.6. Of negative pi over 4 is negative 1. Tangent of 0 is 0. Tangent of pi over 4 is 1. Of 1.2 is 2.6. Of 1.56 is 92.6. So there's some values to use, but we need to think more about the tangent. We just saw that the tangent, this function whose graph we want to come up with, is the ratio sine x over cosine x. What this means is there's going to be a vertical asymptote for the graph of this function for every x for which cosine x is 0. Now, if you think about either the graph of the cosine or what you may have memorized for the cosine itself, there will be vertical asymptotes for this particular function at values of pi over 2 plus, I'm going to write k pi for any integer k. What I'm doing is saying odd integer multiples of pi over 2, or pi over 2 plus pi is 3 pi over 2, 5 pi over 2, 7 pi over 2, and then going in the negative direction, negative pi over 2, negative 3 pi over 2, and so forth. So these are vertical asymptotes, and we draw vertical asymptotes as dashed vertical lines. So let me scale my x-axis with some values of pi over 2 plus pi. Going in the positive direction, I'll put pi over 2 here, and then 3 pi over 2 needs to be a little further down. And then I want to put in the negative direction negative pi over 2. And a little further down, maybe I'll extend this axis a little, negative 3 pi over 2. Now these are values of x for which there are vertical asymptotes. So I need to draw some dashed vertical lines. There's one. Here's another. Here's another. And another. Those are vertical asymptotes for the tangent. Now I have these points that I can plot. Negative 1.56 you can verify is not quite negative pi over 2, and its corresponding y value is very small. That may not quite be on my scale, but I could plot negative 1.2. Let me find the center of this interval, which will be negative pi over 4. Negative 1.2 is a little bit more than that in the negative direction. A little bit less, I guess, would be a better way to say that. Negative 2.6. I'm approximating here. Negative pi over 4 is the center of this piece of my x-axis. That corresponds to negative 1. Then I have the point 0, 0. Positive pi over 4, positive 1. Positive 1.2, positive 2.6, and then this other number that's going to be way off my scale. So the piece of the tangent for which I plotted points, or found table points, looks like that. And that particular piece of the tangent is called its fundamental cycle. It's between negative pi over 2 and pi over 2. And the distance, or the interval here, is pi units long. That's one period of the tangent. And the tangent repeats that shape, let me find the center of this set of asymptotes, between each pair of vertical asymptotes. And the center's over here. And so what I've graphed are 3 periods of the tangent, with the center being called the fundamental cycle. Notice that the range, and let me write that down, of the tangent is negative infinity to infinity. Goes down and up, negative infinity to infinity. Well, let's try graphing another tangent function. What we want to do is determine the period and sketch at least one cycle of the graph of the function y equal tangent 3x. Well, one cycle of the tangent of x, the graph of y equal tan x, had or extended from negative pi over 2 to pi over 2. So what we can do with tangent 3x is consider one cycle between negative pi over 2 and pi over 2 and solve for x by dividing by 3. We see that we want to sketch this between negative pi over 6 and pi over 6. The period of this particular function is going to be twice pi over 6. So the period is going to be 2 times pi over 6, which is pi over 3. And what this piece of information tells us here is that the asymptotes for one particular cycle of this tangent function are at negative pi over 6 and pi over 6. So if we locate those two values on the x-axis, we'll call this one negative pi over 6 and this pi over 6, and draw vertical asymptotes at those, I can sketch the graph of the tangent. That's one cycle, or one period, of the tangent function. Let me point out some other things about this graph. Recall that for y equal tangent x, I graphed the point negative pi over 2, negative 1. This particular function will contain the point negative pi over 12, negative 1, because its period is pi over 3. It'll still contain the point 0, 0, that's the origin, and it will contain the point pi over 12, positive 1. These 2 points are located here as negative pi over 12, negative 1, and here, pi over 12, positive 1. Well, let's move on and look at the graph of the cotangent. as we did before, we want to make a table of values for cotangent of x. And again, using a calculator in radians, if you found the cotangent of 0.02, a very small number, you'd get 49.99. Cotangent of pi over 4 is 1. Cotangent of pi over 2 is 0. Of 3 pi over 4 is -1. And of this other radian angle measure, about -24. Now, I want to think about the cotangent and asymptotes. Recall that the cotangent is cosine over sine. So there will be vertical asymptotes for the cotangent for any value of x for which the sine of x is 0. Well, let's think about that. There will be vertical asymptotes at any value of x for which the sine of x is 0. And if I listed a few of those values first, they would be 0, pi, 2 pi, those are positive values. Going in the other direction, -pi, -2 pi, and so on. And if I think about a way to write those, I can say the vertical asymptotes are either 0 plus k pi. Well, actually, that's a sufficient way to write it, where k is any integer. 0 plus 1 pi, 2 pi, 3 pi, and so forth. -1 pi, -2 pi, and so forth. So to graph the cotangent, I want to start with the vertical asymptotes. So I'll scale my x-axis. 0 is the same as the y-axis. Let's put pi right here, and 2 pi here, and perhaps we ought to label -pi. These are all vertical asymptotes, so I draw them in as dashed lines. And don't forget that the y-axis is also a vertical asymptote for the cotangent. Let's think about the points in our table. This number, just a little bit more than 0, is almost 50, and we probably aren't going to be able to scale that. But at pi over 4, or a quarter of pi, the graph is at 1. At pi over 2, which is half of pi, the graph is at 0. At 3 pi over 4, the graph is at -1. And so this particular piece of the cotangent looks approximately like this. And that's called the fundamental cycle. That particular piece that I've graphed is the fundamental cycle of the cotangent. This is one period of the cotangent. The fundamental cycle extends from 0 to pi. And the cotangent looks like this between every set of vertical asymptotes. So here's another piece of the graph, and here's a third piece of the graph. Let me point out and write down that the range of this is -infinity to infinity, extends to -infinity and to +infinity also. Well, let's continue and look at the following problem. What I want you to do is determine the period and sketch at least one cycle of the graph of the function y equal cotangent x over 2. Pause the video and try this, and when you're finished, restart the video to check your work. Well, let's see how you did. Remember, what we want to do is find the period and sketch at least one cycle of the graph of y equal cotangent x over 2. Well, one cycle of the cotangent of x extends from 0 to pi. So this particular cotangent function, x over 2, will be considered from 0 to pi. And if I multiply each part of this inequality by 2, I can see that x is going to go from 0 to 2 pi. That's one cycle of the cotangent of x over 2. What this tells me is the period of this particular cotangent is 2 pi. The asymptotes will be at 0 and 2 pi. So let me label 2 pi here. Remember, 0 is the y-axis. And draw a vertical asymptote. And between these two vertical asymptotes, sketch a graph that looks like the cotangent function. Well, let's continue by looking at the graph of the secant function. What we want to do is graph y equals secant x. To do this particular graph, recall that the secant is 1 over the cosine. So again, we have this situation where there are asymptotes. There are vertical asymptotes for the secant at any x for which the cosine is 0. A way to get the graph of the secant, is to actually graph the cosine, and I'll go ahead and start by graphing that. Recall that, let me scale my x-axis first to pi and 2 pi, negative pi and negative 2 pi. So I'm going to graph just the cosine, not the secant for the time being. The cosine of 0 is 1, of pi is going to be negative 1, of pi over 2 is 0, and let's see, is 0 here and positive 1 there. So here's part of the graph of the cosine, and it repeats that going the other direction, in the negative direction. So here's another piece of the graph of the cosine, not the secant. Now if we look at this ratio, the secant has a vertical asymptote at any x for which the cosine is 0. Notice that the zeros are the same as the x-intercepts. And so we can draw, once we have the cosine, the vertical asymptotes for the secant. And here's one more. And then to sketch the graph of the secant does the following. And one more piece. So these pieces are the graph of y equals secant x. You know what the graph of cosine x looks like, so ignore that piece and consider the other pieces, curves, the graph of the secant. Let's write down its range and make note of that. The range of the secant, if you see that if this particular point is 1 in the y direction and negative 1 is here, the secant extends from negative infinity to negative 1 and from positive 1 to positive infinity. Well, let's do something similar for the graph of the cosecant. Recall that the cosecant is the reciprocal of the sine. So there's going to be a vertical asymptote at any x for which the sine is 0, and we can find those most simply by graphing the sine function. So again, we want to scale our axis accordingly because we want to graph the sine. That's negative pi, negative 2 pi, and the sine of 0 is 0, of pi over 2 is 1, of pi is 0, of 3 pi over 2 is negative 1, and 2 pi is 0. So one piece of the sine looks like that, and it does the same behavior in the negative direction. This is not the graph of the cosecant. That's supposed to be curved right there. That's the graph of the sine. But what this gives us is the vertical asymptotes for the cosecant, because at every x-intercept, or every 0 of the sine, there is a vertical asymptote for the cosecant. One of them is the y-axis. Here's another, and here's another. And then the graph of the cosecant does the following. In between each pair of vertical asymptotes. And I should point out that the period of the cosecant matches the period of the sine, as did the secant, by the way. And the range of the cosecant is from negative infinity to negative 1 and positive 1 to positive infinity. So we can write the range, negative infinity to negative 1, union, positive 1 positive infinity. Well, let's try one more graph. Let's do the following. We want to determine the period and sketch at least one cycle of the graph of y equal cosecant of 2x minus pi over 2 and state the range. Well, let's consider this. We want to graph cosecant 2x minus pi over 2, and the cosecant is the reciprocal of the sine, so this is 1 over the sine of 2x minus pi over 2. Now I want to factor a 2 from the parentheses here, so I have sine of 2 times x minus pi over 4. That helps me because considering the graph of the sine, I can now see that the sine function's period is 2 pi over 2, or pi, so the period of this function is going to be pi. And it also tells me there's a phase shift of pi over 4 units. So the fundamental cycle of the sine, if we consider that for the moment, is period, or has period pi, and extends from, let me write it this way, fundamental cycle is from pi over 4 and extends pi units, so goes to 5 pi over 4. Since I only want to draw one cycle, I'm going to draw this particular cycle. I know that it goes from pi over 4 to 5 pi over 4, so let's scale our axis accordingly. Let me put pi over 4 right here, and 5 pi over 4, and the center of those is going to be 3 pi over 4. Now, if I were going to draw the sine, I would draw a familiar sine wave. Now, I'm not going to draw the sine, but I want to use those values as vertical asymptotes for this cosecant. So here are the vertical asymptotes for the cosecant. And recall again, think in your head what the sine function looks like, and draw, let me label 1 and -1, and draw the cosecant accordingly. There's one piece of the cosecant, and there's another piece of the cosecant. Well, in this lesson, we've looked at the tangent, cotangent, secant, and cosecant functions. Be sure to work lots of exercises for practice.